Good morning, cadets. Today we are going to learn about the motion of charge particle in a magnetic field. Before we learn the motion of charge particle in a magnetic field, let us solve some simple problem. There is a current carrying conductor of certain length 1.5 meter. This current carrying conductor is suspended in mid-air due to a strong magnetic field, and the length of the conductor is 1.5 meter, and it carries a current 2 amperes. 2 ampere of current is flowing through the conductor. This is of mass 200 gram. Mass of this straight wire is 200 gram. It is suspended in mid-air by uniform horizontal magnetic field. Then, what is the magnitude of magnetic field? This is the question. It is suspended in mid-air by strength of a uniform magnetic field due to its magnetic force. So, you are asked to find out what is the value of that magnetic field, magnitude of magnetic field. So, here whenever a mass is taken, a wire is taken, when you just leave it in the air, it falls. It falls down due to the gravity. So, always its weight is acting vertically downwards. When it is held mid-air due to magnetic force, it means there must be magnetic force which is acting vertically upwards. So, the magnetic force, if it is acting vertically upwards, then what should be the direction of magnetic field? That is the question. Let us assume that the 2 ampere of current is flowing in this direction from left to right, and the length of this conductor is, as it is given, 1.5 meter. So, this is a current carrying conductor held in a magnetic field. The question arises, what should be the direction of magnetic field? Right? We will find out the value of magnetic field. So, the magnetic force is vertically upwards. So, we need to use Fleming's left hand rule. What Fleming's left hand rule says? Stretch first 3 fingers of your left hand mutually perpendicular to each other. First 3 fingers, thumb, forefinger and the central finger. The forefinger shows the direction of field. F for field, just remember, forefinger for field. Then the mutually perpendicular central finger for current. Central finger for current. Then you see, perpendicular to these two, there is a thumb. The thumb shows the direction of magnetic force. Thumb, T-H-U-M-B, M, stress on M. M for mechanical force. Mechanical force experienced by current carrying conductor in the magnetic field. So, thumb. So, I am writing M capital so that you can understand magnetic force or mechanical force. Magnetic force. And this field is magnetic field. So, this is Fleming's left hand thumb rule, FLHT rule. Fleming's left hand thumb rule, right? Now, I am using my left hand. First 3 fingers are being stretched mutually perpendicular to each other. You see the central finger. The central finger is pointing in the direction of flow of charges, that is direction of flow of positive charges, that is direction of current. So, this gives you direction of IL, right? And the field should be, see, in order to have the thumb vertically upward, the field, you see, the field forefinger should be pointing vertically inwards. So magnetic field is acting vertically inwards. So direction of field is shown by cross. So this is understood. So there is a uniform magnetic field acting vertically inwards, perpendicular to the plane. So the thumb shows the direction of magnetic force experienced by the current carrying conductor. So that the magnetic force due to this magnetic field balances the weight of the wire itself, so that it is held suspended freely in mid-air, right? Now we can calculate the magnetic field using the force experienced by current carrying conductor. You see here, force experienced by current carrying conductor is given by IL cross B, as we have studied earlier. But here magnetic field is taken perpendicular to the current element. IL is called as current element, current wire. IL together is a vector which is taken as current element or current wire. So IL cross B. So when they are perpendicular to each other, then it is understood that ILB sine 90, the angle between magnetic field and the current element is 90 degree, therefore it becomes ILB. Therefore F is equal to ILB. This is Lorentz force experienced by current carrying conductor. Now this F should be balancing weight. F should be balancing weight. Weight of a body is given by mg. Therefore we get the equation mg should be equal to ILB, or ILB should be equal to mg. So using this we can very easily get the value of magnetic field. Therefore ILB, magnetic force, balances the weight mg. Therefore B is equal to mg upon IL. Very simple. Just substitute the values. M is given 200 gram. Convert this 200 gram into SI unit, that is kg. So it becomes 0.2 kg. Okay. Just substitute 0.2 kg multiplied by 9.8 meter per second square, that is acceleration due to gravity, by current is 2 ampere. So 2 ampere multiplied by the length is 1.5. So you can just shift the decimal point, it becomes 2 upon 15. So 2 cancels. So you are left with 9.8 divided by 15. This is the magnetic field in terms of Tesla. So if you calculate, it comes out to be 10 by 15 approximately. That is 2/3 of a Tesla. 2 by 3. 5 2s are 5 3s are. So 2 by 3 Tesla. So that comes out to be almost 0.65 Tesla. So this is the value of magnetic field, that is magnitude of magnetic field. And what is the direction? Direction of magnetic field B vector acts vertically inwards, perpendicular to the plane of the board, perpendicular to the plane of the board. So please remember the cross mark shows the tail end of the arrow. Cross mark shows the tail end of the arrow. If magnetic field is acting towards me, then I will be seeing the pointed end of the arrow. So I will be seeing the pointed end of the arrow. In that case, it is shown by just a dot like this. So dot shows the arrow pointing outwards. The cross shows the tail end of the arrow pointing inwards. So these are the symbols for magnetic field, right? Pointing inwards and pointing outwards. Now this is one simple problem which we got it as magnitude of magnetic field. In the same way, there is one more problem from your textbook, that is about again moving charge in a magnetic field, right? Let us solve that second problem also. See this second problem. This is from your textbook 4.2, example number 4.2. There is a charged particle moving along positive x-axis, and you see the cross marks representing a uniform magnetic field acting perpendicular to x-axis. Let us say it is acting along y-axis. Then what is the direction of magnetic force experienced by the charged particle? So there are two cases. What happens if a positive charge moves with some velocity along the positive x-axis perpendicular to the magnetic field in this way? Magnetic field is acting along y-axis. I have shown y-axis. This is the direction of y-axis. It is pointing vertically inwards. Arrow marks, as I have shown you, the cross mark shows the direction of magnetic field pointing inwards. Then what is the force experienced by this positive charge, if it is a positive charge or a proton moving with some velocity? If this proton is replaced by an electron, then what is the force experienced by that electron? This is the question. So first let us see what happens if a proton is moving with some velocity vector v along the direction of positive x-axis. Then it experiences Lorentz force. As I have said, use first three fingers of your left hand and apply Fleming's left hand thumb rule. Fleming's left hand thumb rule. So the field, you see, forefinger shows the direction of field. The forefinger is acting vertically inwards, and the central finger shows the direction of motion of positive charges, that is the direction of current motion of positive charges. And see the thumb acts vertically upwards. Therefore, if it is a positive charge like a proton is a positively charged particle. If a proton is moving with some velocity vector, it experiences a Lorentz force, a magnetic force due to this magnetic field vertically upwards along positive z axis. Therefore, I have written if plus q charge moves along positive x axis, it experiences Lorentz force F is equal to qvb k cap, where k cap shows the direction of z axis. Because velocity vector is along x axis, b vector is along y axis, v cross b gives you vb sin 90, because the angle between x axis and y axis is 90 degree. Therefore, it becomes qvb, but the direction of v cross b is perpendicular to both v and b. Therefore, f vector acts perpendicular to both velocity vector and b vector, which is obviously the z axis. So k cap represents the direction of magnetic force experienced by proton, a positively charged particle moving with some velocity v. Second case, let us say now instead of proton, if it is a electron, moving along positive x-axis. If the electron moves along a positive x-axis, then what is the force experienced by electron? Electron is a negatively charged particle having the same charge as that of the proton, right? Then it also experiences a Lorentz force. Now, if electron is moving along positive x-axis, it is as good as assuming same amount of positive charge is moving along negative x-axis. Means now velocity vector of the positive particle will be along negative x-axis, Then the central finger, you see, the central finger should be taken along negative x-axis. The forefinger, you see, it is as shown acting vertically inwards. This is central finger, this is forefinger, index finger acting vertically inwards. You see the thumb points vertically downwards. So this is the force experienced by the electron, which is vertically downwards acting along negative z axis. So if minus q, that is, let us say minus e charge, that is electron moving along positive x axis, then the force experienced by that negative charge is F is equal to qvb, same, but the direction of force is now pointing vertically downwards, as I have shown you, vertically downwards. As a result, you see it becomes minus k. So it acts along negative z axis. So sign convention is very, very important. Okay, that's how we apply Fleming's left hand rule in order to find out the force experienced by charge when it is moving in a magnetic field. or force experienced by a current carrying conductor IL placed in a magnetic field B. So, that is also F equal to IL cross B, that is Lorentz force. So, for both the cases it is Fleming's left hand rule. Okay. Now, let us study motion of a charge particle in a magnetic field. Two cases are there. What happens when the charge particle is moving with some velocity vector in a uniform magnetic field which is acting perpendicular to the direction of velocity vector? Then naturally it experiences a Lorentz force, a sideway force, which is found out using the Fleming's left hand rule, right? It is very interesting. Let us see. Let us consider a perpendicular magnetic field. Now, we are studying motion of a charge in a magnetic field. The first case is when velocity vector of the charge particle is perpendicular to the magnetic field. So, this is first case, velocity vector perpendicular to magnetic field. And the magnetic field here, as I have shown you, it is a uniform magnetic field. You see the field lines are shown perpendicular to the plane of the board, pointing vertically inwards, so that we can see their tail ends cross marks vertically inwards. This is a uniform magnetic field, parallel magnetic fields acting vertically inwards. Now, suppose a charge particle enters with velocity vector v inside. If a charge particle enters with velocity vector v inside, you see, then this charge particle q having velocity vector v experiences a Lorentz force, magnetic force due to this magnetic field. Then to find the magnetic force, we apply Fleming's left hand thumb rule. Again, stretch your first three fingers mutually perpendicular to each other to show the field direction using forefinger, central finger to show the direction of velocity vector or current vector. The thumb, we see the thumb is pointing upwards. So, this charge particle experiences a magnetic force which is acting perpendicular. So, due to this perpendicular force F, the charge particle undergoes deviation. Instead of going along straight path, it undergoes deviation. As a result, you see that it deviates from its path. So, when it is at this particular position, suppose it has reached this particular position, then draw the tangent. The tangent at this point gives you direction of its velocity vector. Then again you see, if you apply Lorentz force, it experiences a sideway force. The sideway force is again perpendicular to this velocity vector, and this gives you direction of force. As a result, this particle again deviates further. Instead of going straight, it deviates further, undergoes deflection. In this way, it almost undergoes a circular path, and then it completes a circular motion like this. So, it keeps on undergoing circular motion in this fashion. The reason behind this is the Lorentz force. The Lorentz force is acting everywhere. For example, if it has reached here, if you draw a tangent, so tangent gives you direction of velocity vector, and the force is always acting perpendicular to this, again applying Fleming's left hand rule. So, everywhere the charge particle experiences Lorentz force which is acting inwards. So, thus the particle undergoes what is known as a circular motion. So, a charge particle moving with some velocity vector v in a perpendicular magnetic field undergoes rotational or circular motion. It revolves with some fixed radius. It undergoes a circular motion about a common center with some radius, let us say r. So, the reason behind it, as you have followed here, is the Lorentz force. Every point there is Lorentz force acting on it. See here, if plus q charge moving with velocity vector v in a perpendicular magnetic field B, uniform magnetic field B, it experiences magnetic force F is equal to QV cross B. QV cross B. So, angle between velocity vector and magnetic field vector being 90 degree. So, it simply becomes QV sin 90. So, QVB sin 90 becomes QVB into 1, that is QVB. So, direction is given by n cap. N cap is perpendicular to both velocity vector and magnetic field vector. Now, this force provides necessary centripetal force. This provides necessary centripetal force because the charge particle, when you say that it is charge particle is experiencing, you can see that everywhere it is the force acting radially inwards. So, when the charge particle is undergoing circular motion, there should be some centripetal force, and that centripetal force is provided by the Lorentz force, which is QEB. This Lorentz force provides necessary centripetal force. We know expression for centripetal force is given by mv square by r, mv square by r, where r is the radius, v is the velocity, and m is the mass of the charge particle, where m is mass of the charge particle and r is radius of circular path. So, because of this Lorentz force acting at every position, the particle undergoes circular motion. Now, we can calculate what is the value of radius of this circular path, equating these two forces, because centripetal force is provided by Lorentz force. So, that implies mv square by r is equal to the Lorentz force QVB. So, v cancels. When you cancel one v, you are left with only one v. Therefore, radius r becomes equal to, you can see, mv upon qb. So, where r gives you radius of circular path. Radius of circular path. Now, since the charge particle is entering with uniform velocity, means constant velocity, as it is experiencing a magnetic force due to uniform magnetic field. So, the force is always perpendicular to the velocity vector. So, the force is always perpendicular to the tangent. The force acting perpendicular to the tangent must be acting along the radius. So, everywhere you can see the force is acting radially inwards. Therefore, it is a radial force which we have called it as centripetal force provided by Lorentz force. So, that keeps the charge particle to revolve with constant speed. Its direction keeps on changing everywhere, but its speed remaining constant. Thus, it undergoes uniform circular motion. Now, if you calculate the work done by this Lorentz force, to keep the charge particle in uniform circular motion is 0. Reason is force is perpendicular to velocity vector. So, everywhere you see the radius is perpendicular to the tangent. So, force is always perpendicular to the velocity vector, force is always perpendicular to the displacement. Therefore, work done by the Lorentz force is 0. Therefore, only the direction of velocity vector changes, but the magnitude of velocity remains constant. Therefore, the charge particle undergoes uniform circular motion. So, that is how we get the radius of circular path. So, from this equation it is evident that radius of circular path is directly proportional to momentum of the particle. It is directly proportional to velocity, it is directly proportional to mass of the charged particle. If velocity of the charged particle is high, then the radius of the circular path is also large. If velocity is less, if it enters with less velocity, its radius of revolution is also less. That is the meaning of this. Then R is also inversely proportional to the magnetic field. Larger the strength of magnetic field, higher the strength of magnetic field, right? Shorter is the radius of circular path. Lesser the strength of magnetic field, larger is the radius of circular path. That's how radius is inversely proportional to magnetic field B. These are the 2 points to be remembered. And it depends inversely proportional to the charge Q. R is inversely proportional to charge Q. More the amount of charge, less is the radius of circular path. That's the meaning. Lesser the amount of charge, larger is the radius, right? Inversely proportional to charge. And it is directly proportional to mass. Already it is being written. Now using this, we can now write the expression for angular frequency, right? Angular frequency is given by omega. We know that the relation between angular velocity and linear velocity v equal to omega r. So this implies omega is equal to v by r. So using this I can find out what is omega. Omega is thus, we can write what is omega. Omega is equal to v by r qb upon m. So v by r from this equation implies omega is equal to qb upon m. Means angular frequency is equal to qb upon m. So more than the angular frequency, we are interested in frequency, number of revolutions per second, number of number of cycles per second. So we know another equation for omega. Omega is also equal to 2 pi nu, where nu is the linear frequency, omega is the angular frequency. Therefore, this implies 2 pi nu is equal to qb upon m. So that implies nu is equal to, right, qb upon 2 pi m. So this gives you frequency, number of revolutions per second, that is called as frequency. So frequency is denoted by nu. So this is very interesting here, that frequency is independent of velocity, frequency is independent of radius. So frequency is directly proportional to strength of the magnetic field. Frequency is directly proportional to the charge of the particle. Frequency is inversely proportional to mass of the particle. So frequency is nothing but number of cycles per second in a given strength of magnetic field. So frequency nu is directly proportional to B. Frequency nu is directly proportional to charge, or you can also write charge by mass. Charge by mass ratio is called as specific charge. It is directly proportional to charge by mass, specific charge, right? So larger the charge by mass ratio, larger the specific charge, more is the frequency. So this actually becomes the principle of what is known as cyclotron. Cyclotron is a particle accelerator in which the positively charged particles get accelerated to a higher and higher velocity. So when the charged particle comes out of the device called cyclotron, it possesses maximum kinetic energy. So cyclotron is a particle accelerator especially used for accelerating positively charged particle, right? So when the charged particle comes out of this cyclotron, the charged particle possesses maximum velocity, thereby it possesses maximum kinetic energy. So the principle of cyclotron is this, that frequency of the charged particle undergoing cyclic motion or revolutional motion is independent of its radius or its velocity. Okay, it just depends on strength of the magnetic field. Thank you. Have a nice day. Bye.